So permutations can be of two general kinds. You have the single case permutations, which is what we're going to look at in this video in more detail. And then you have the permutations with multiple cases, and that'll be a different video altogether. Now, when it comes to the permutations that are single cases, they fall into two general categories. One's where repetition is allowed. So we write repetition is allowed. And then the other category that has restrictions. And that would be where repetition would not be allowed, for example. So we're going to tackle a couple of problems from each case. So sometimes we have permutations that have identical or repeated objects within the set. And so when you have permutations with identical objects or repeated objects in a set, the formula is going to change a little bit, where we can have permutations of identical objects is equal to the factorial, n factorial, which would refer to all objects in the set, right, or number of objects in the set, divided by r factorial, and this would be the number of repeated objects. And let's say I have more than one object that repeats or that's identical in a set, then I would just simply keep adding it onto this here. So for example, let's say I had a set where, let's say out of 5, right, so it'd be 5 factorial would be the number of objects in the set, and then there's a repeat of 2, and then another repeat of 2, and then there's only 1. Well, it would go like this. So I would go, if I wanted to figure out the number of permutations in that set with those identical objects, I would go 5 factorial over, and then it would be 2 factorial multiplied by 2 factorial. So in our first example, how many ways can the letters in the word Mississauga be arranged? Well, I know that this falls into the permutations of identical objects because I could see that there's a repeat of the S and there's a repeat of the I's and as well a repeat of the A. So because we have, I guess, 3 sets of identical objects, then we're going to use the formula listed above. So the number of letters in this entire set is 11, so it'll be 11 factorial. And then now, there are 4 repeats of S, there are 2 repeats of I, and 2 repeats of A. And so, we go 11 factorial over 4 factorial times 2 factorial times 2 factorial. And then when you plug this into your calculator, you should get the following. And that would leave us with about 415,800 ways that the letters Mississauga can be rearranged. For the second example here, a multiple choice test has 10 questions. 3 questions have an answer of A, 4 questions have an answer of B, 1 question has an answer of C, and 2 questions have an answer of D. How many unique answer keys are possible? So remember, unique is always going to signify that we're dealing with a permutation over here. So again, I can see that the repeats or the identical objects in this set are A and as well B. There's a repeat of 3 for A and a repeat of 4 for B. So then automatically we know that we're going to use this permutation formula, n factorial over r factorial. And the n factorial would be 10 over here since there are potentially 10 questions. And that's going to be divided by 4 factorial for B multiplied by 3 factorial for A. Now the order doesn't really matter here in terms of whether I write the 3 first or the 4. So don't get fretted about that. And then another repeat is 2 questions for D. And this gives us a total of 12,600 unique ways or unique answer keys that are possible for this test. I'm going to just highlight this right over here. The permutations formula used when R things from N things have to be arranged with repetitions is the following, where it's N times N times N, and then we carry on for as many repetitions as follows, or as many objects that are labeled as R or that are chosen from the set as there needs to be. What we mean is that if there was an R value of 5, you would just multiply N by 5 times. Now this can also be rewritten, some people choose to do it this way, as N to the R. Again, depending on whatever the R value is. How many two-letter words can be created using the letters A, B, C, and D? So in this case, we are allowing repetition. It does not indicate in the question that, no letters can be repeated, etc. So we know that we are using the formula that allows for repetition, etc. Now, the events that you're choosing are the two letters that make the word. So you're essentially choosing two things, or there's two cases here. So what we're going to do is we're going to make two lines over here, and that'll be, one letter, and then this is the second letter, and together they're going to make a word. And because of the letters provided, and we're allowed to have repeats, that means that for each event, there's an equal opportunity of, or I should say equal possibilities of 4. And that's because even if you use a letter up for your first letter, you're still allowed to repeat that letter again. And so you're not going to take anything away or any choices away from the second. So we got 4 times 4. And then this is going to give us, of course, 16 possible two-letter words. Now, if I'm looking at the exponential formula, well, my permutation, in this case, can be N to the R, which, of course, out of 4 letters, you're choosing 2. You're picking 2 out of 4, and, of course, that would give the same answer. A coat hanger has 4 knobs, and each knob can be painted any color. If 6 different colors of paint are available, how many ways can the knobs be painted? Now, because it says that the colors, or I should say, because it doesn't say that the colors can't be repeated, we can assume that repetition is allowed. So we are also going to use the N times N times N, etc., up to how many R's are chosen, or objects are chosen from this set, or the exponential version as well. Now, our N value here would be these 6 different colors, because the colors of the knobs will come from the colors themselves. It won't be the colors that come from the knobs. So we're going to choose 4 knobs to be painted from the 6 colors that are available. Now, each knob, so if this is first, second, third, and fourth knob, you're allowed to have any of the 6 colors applied to it. And you can repeat the color of the previous knob if you would like. So that doesn't take away the amount of choices available for each of the knobs. And since over here, we got 6 times 6 times 6 times 6, that would give us about 1,296 possible ways that the knobs can be painted. Now, if we use the exponential, well, again, same thing. From the 6 colors, we're choosing to paint 4 knobs, and 6 to the 4 gives us 1,296 ways as well. A phone number in British Columbia consists of one of 4 area codes, 236, 250, 604, and 778, followed by a 7-digit number that cannot begin with 0. So I'm going to write, because this can often be overlooked, we're going to write cannot begin with 0 or 1. How many unique phone numbers are there? Now, that means outside of the first number, there are generally 10 numbers to choose from, right? If we think about from 0 to 9, that's 10 numbers. So we're going to say that from basically 10 numbers, if I'm thinking about 7 digits followed by the area code, that'll be a total of 10. So from 10 numbers, we're going to choose 7. But what I will also do is, from the 4 area codes, I'm going to choose one of them. So that really leaves me with 8 choices in total. Now, so we'll start with the red over here. So from 4, I'm choosing one of them. Now, the first one cannot begin with a 0 or 1. So that means that out of the 10 numbers, I should say, we're going to be choosing 8 of them. But then the rest of them, you're allowed to choose a 0 or 1 all the way up to 9. So the rest of them will have all 10 options available to them. And that's because repetition is allowed. So we would go 4 times 8 times 10 times 10 times 10 times 10 times 10. And that would give us a total of 32 times 10 to the 6 unique phone numbers.